All right, and welcome back, everyone. So in the previous video, we derived this formula for how to solve our first order linear equation in standard form, right? So this guy up here, standard form, I'll make sure it's the only equation on the page, yeah, at the top. This is the standard form of the first order linear differential, ordinary differential equation. And we actually came up with an explicit formula that tells us exactly how to solve this thing when we know what these function coefficients look like, or these coefficient functions, excuse me, what these guys look like. And I thought it would be a good idea to walk through a couple of examples. And the two examples that I have in my notes here are just to really illustrate that this is kind of an unavoidable technique that you really do need to know how this guy works, especially since most differential equations are not separable and we can't actually use our original method for solving our rate equations when they usually look like this guy. dy dt is equal to a function of t by y. There we go. So this is nice. I mean, we can go ahead and actually see that this takes the correct form, but this function may not actually be just a function of t or a function of y or a product thereof. No, it's actually going to wind up being more of the case that you wind up with equations like these that cannot be separated. So what we have to do instead is put this into standard form. And when we do that, we notice, if I'll bring the equation back up here, we are in the clear that there is a 1 sitting in front of this derivative term. Great. So the question now is, what's p and what's q? Well, do be careful here. This is really plus -1 times y, and then there is the x floating around on the right side. So that means, in this case, p of x is going to be the constant function -1, and q of x will just be the entire right-hand side, which is just the function x. Great. So that information aside, we know exactly what our integrating factor has to look like. This is e to the integral of p of x dx. And in this case, this is e to the integral of -1 dx, which is just going to be e to the minus x. So this is the function that I should multiply in to both sides of this standard form differential equation. So let's do it. This is e to the minus x, and I'll use prime notation, minus e to the minus x times y, and that should be equal to e or x times e to the minus x. Great. Wonderful. What was the point of that? Well, if we take a look at the left-hand side, we can observe this is exactly what happens when you differentiate and use the product rule on e to the minus x times y. Go ahead and double check this, right? And make sure that if you differentiate the product, you actually wind up with this thing in the curly brace, right? Math is not a spectator sport. Make sure you got a pencil and paper handy as you're walking through these yourself. So that means that all we have to do now is integrate both sides of this equation. And on the left side, we actually luck out. It's the integral of a derivative, and we're done. Right-hand side, okay, this is where things get a little tricky. I still need to integrate x times e to the minus x dx. Okay, yes, you are going to have to remember how to integrate stuff from Calc 2. Okay, and you might remember that integrating this particular kind of function, integrating a product of functions, is actually best suited for integration by parts. And I do this as tabular integration. So I'm going to be differentiating down the left-hand side, adding a plus and minus pattern. And then I'll be integrating down the right side. So I integrate and wind up with a minus e to the minus x. And then I pick up another minus sign, so they cancel, and I wind up with an e to the x, or e to the minus x. And then I multiply down the diagonal, right? Each block here. Yeah, let me think about this. Yeah, I'll explain that in a second. But I'm multiplying down and then integrating over in the last line. So that means that this right-hand side is going to be this product, so minus x, or I'll do it in the order that it's presented, x times minus e to the minus x, minus 1 times e to the minus x, and then plus the integral of 0 times e to the minus x. Integral of 0 is a constant, so this actually picks up the plus c term as well. This is why I really like tabular integration. So let's see. That means that we have e to the minus x times y needs to equal this right-hand side. So in order to pick up y of x, I just have to multiply by e to the minus x, or e to the x, or divide by e to the minus x, however you want to see it. But that means I wind up with minus x minus 1 plus c times e to the x. And that completely solves, with a general solution, the differential equation up here that we started with. And we can check this, right? So check. What's the derivative here? Y prime, this is going to be a minus 1 plus a 0 plus c e to the x. Y, okay, I don't need y. Well, no, I do. Y is equal to x minus 1 plus c e to the x. And I ask myself, what happens if I look at the left-hand side here, or if I just look at the right? So the derivative of y here, this is equal to what happens when I take y and add x to both sides. And sure enough, that'll be on the right-hand side, minus 1 plus c e to the x. So yeah, I buy that. Y prime is equal to x plus y. Sure, and that works for any choice of c. Right, and remember, c is just going to be some arbitrary constant until you input an initial condition. And we will actually see that in the next example, if I remember correctly. Yes, that's an initial value problem in the next example. So let's do an initial value problem. Let's see what happens when you impose an initial condition. So I have the following equation. So 1 plus x squared times y prime plus 2y is equal to 1. And I'm going to use the initial condition, y of 0 is equal to 2. So in other words, if I use x equals 0 and y equals 2, I should be able to find a specific value of c to pin down exactly one solution and not a general solution like this guy to this differential equation. But the problem with me starting this is that this 1 plus x squared times y prime plus 2y, this equation is not in standard form. In order for me to have this in standard form, I can't have this 1 plus x squared floating around in front. So I have to divide the entire equation by 1 plus x squared. And when I do, this will now be in the standard form. And in this case, here's p of x, and over here is q of x. That means that mu is equal to the integral, or e to the integral of 1 plus x squared dx. And in this case, this is e to the 2 times the arctangent of x. And notice I'm dropping all of my plus c integration factor or integration constants here because I don't need them. I just need a single mu function to make this work. And this is one that does it. And I can show you. Look what happens when I multiply in. Well, I don't even have to multiply it in at this point. I know what has to happen. This will be e to the twice arctangent of x times y prime. And this will equal what happens when I multiply the right-hand side by e to the twice inverse tangent of x. All right. So on the right-hand side, well, actually, let's integrate. On the left-hand side, super easy. E to the twice arctangent of x times y. On the right-hand side, I actually have exactly what I need for a chain rule. So in this case, you can, or not a chain rule, yes. So you can use a u substitution here on twice arctangent of x and wind up with 1/2 e to the 2 arctangent x plus a constant. And sure enough, if I go through and divide by this exponential, I'll wind up with 1/2 plus some constant c times e to the minus 2 arctan of x. And this is the general solution. But remember, I have an initial condition, so I can actually use that initial condition to find what this c has to be. So if I use y equals 2, oh, son of a gun, get out of here. If I use y equals 2 and x equals 0, minus twice arctangent of 0. Okay, come on, people at home, say it with me. Arctangent of 0 is, yes, it is 0. Very good. So c times e to the 0. So this is 2 equals 1/2 plus c. So that means that c has to be 3/2. And I plug this in upstairs, and I have y of x equals 1/2 plus 3/2 e to the minus twice arctangent of x. And that is what we call a particular solution to the differential equation. And you always get a particular solution when you have initial conditions, because there is exactly one solution that will satisfy this, this equation. And yes, we will prove that. We will demonstrate that that is the case. If there is a solution, then it is the only one when you have certain conditions on your rate function. But that, I think, is good for this video, that we are now complete masters of first-order linear equations. And then I'm looking through my notes here to see what the last little bit is. Yeah. You know what? Yeah. We'll do that in the next